we'll use the von Neumann. I'm not sure what number of ends, so I'm ambiguous. Okay, and I'm going to define, okay, so the divergence between sigma p and sigma q being the trace of sigma p times log of sigma p minus log of sigma q. Okay, so here, the logarithm is the logarithm of a matrix. So you keep the eigenvectors and you apply the log to the eigenvalues. Do this for sigma p, do this for sigma q, and you compute this. And I think this is from the 20s. Okay, 1920s. Okay, and all right. So we're going to do that. We're going to assume that phi of x comes from a kernel. So this comes from a kernel. So typically like infinite dimensional. So we're going to move from matrices to operators, but this is what quantum mechanics is doing anyway. And we're going to to call that the kernel relative entropy, just to give it a name. Okay, and one thing that I mentioned now before I forget is that, so here you can think of the kernel in -1, 1 to the d, on the hypercube, can be for discrete data, could be for graphs, so you can leverage all the nice way from kernel methods to apply this to any problem. Okay, but I'm going to focus mostly on RD here. Okay, so a few properties. So mostly properties of the von Neumann relative entropy. So one, and it's jointly convex in sigma p and sigma q. Okay, and so this is a highly non-trivial fact. So proving this is already like quite involved. Okay, so convexity with respect to sigma p is kind of natural because this is a spectral function which is a convex function. But joint convexity is really complicated, and there are lots of papers coming from physics dealing with this. Jointly convex, sorry. Okay, and because sigma p and sigma q are linear in P and Q, you get like joint convexity in P and Q. So you preserve the nice aspect that you have with the regular relative entropy. So it's positive and 0 if and only if P equals Q. Okay, so this is just a consequence that is the Riemann divergence for the trace of sigma log sigma. So it's positive and equal to 0 if only if sigma p is equal to sigma q. But because I've assumed my kernel is universal, sigma p being equal to sigma q is like p equal to q. Okay, so this is like simple things. And also for those who are worried about definitions, like Florent, it's finite. Okay, with like simple conditions on P and Q. On P and Q. So here for me, if it's finite, it's well defined. If it's not finite, it's not well defined. But typically, if dP over dQ is bounded, you can show it's already well defined. Okay, so but I'm not going to worry too much about those problems. All right. A few other properties, which are those ones are just like consequences or well-known properties of the von Neumann entropy. What is not as well known, so let me. What is not what I worked on is the proposition estimation from finite samples. Okay, so here, why is it important? Is because so I'm defining an object in infinite dimensions. Okay, so I have to compute the moment matrix. I have to diagonalize it, compute that. So clearly, you need a way to compute it. And it turns out that so you assume sigma q is known, so like because it's let's say uniform distribution, so a simple one, and you have x1 xn sample from P. And you want to check that you can estimate it. And so then you can define the natural estimator, sigma p hat, which is just the empirical moment. Okay, so fear xi transpose. And it turns out that if you just do the plugin estimator of sigma p hat onto here, you get that d of sigma p hat sigma pq minus d of sigma p sigma q is up to 1 over root n. Okay, so this is, of course, there are conditions on the kernel. It has to have a sufficiently strong decay eigenvalues, but quite reasonable. And so you obtain like the nice 1 over root n convergence. Okay, so here I'm not going to give you the details, but that's, and the big O is, well, the O constant, the big O, is just to highlight the fact that we can estimate it from samples. Okay. And the reason I'm doing this is to compare to MMD.
So do you have to regularize somehow, Darren?
Ah, very good question. And I was surprised that the answer is no. You can just do the plugin. Okay, you can do the plugin and you get a big O of 1 over n. Also, didn't mention it, but you can kernelize the estimation. Okay, once you have that, it's essentially computing the trace of k log k when k is the kernel matrix. But you don't need to regularize, right? Which is kind of amazing because you're going to have issues when the eigenvalue goes to 0. But magically, if the decay of the spectrum is strong enough, like 1 over power of 4 is enough to have the estimation. You can look at the paper to get the. It's essentially leveraging like properties of the degrees of freedom of kernel methods. It's a bit involved, so I won't cover it. But I want to compare to MMD, which you're probably aware of. What is MMD? You define instead mu p is 1 over n. No, is the integral of phi of x dpx. Okay, and remember that sigma p was the integral of phi of x transpose dpx. And what is MMD? MMD between p and q is just the norm between mu p and mu q. And essentially, all the properties I've described so far for this new kernel entropy are shared by MMD. Totally convex in P and Q, this is still true. 0 positive is P equal to Q, this is true as well if you're universal. This is always true. You can estimate 1 over root n. Okay, so all the properties are the same. Okay, so you may think that why bother looking at something more different. Yeah.
What does it stand for? MMD?
Maximum mean discrepancy.
Oh, okay.
It's like, I think the references is like Breton, Arthur Breton. Okay, and in the paper I mentioned there's a nice tutorial by Mirande, which is quite nice to learn about that. So MMD has a similar purposes, okay, and but there's one key issue is that there are no links whatsoever with the classical notions of divergences from information theory. Okay, so essentially, in the classical case, it's just the L2 norm between like smooth densities, which is not very far from entropy. So what will be nice with this one is that there will be a directly with entropy, which I will now give, like a very, very direct. Let's look at that link. And it's going to be, so the link entropy. Okay, so assumption. So here will be a single assumption is that for all x in my set, the norm of the features are less than 1. Okay, I'm just assuming this. Okay, bounded feature with norm less than 1. So let's look at d of sigma p sigma q. Alright. So the formula is so this is the divergence between the integral of phi of x phi of x transpose dp of x, and the integral of phi of x transpose dqx. So let me write dqx as dq over dp, okay, of x dpx. Okay. Check I'm starting correctly. I'm starting correctly. Yeah, but before I do that, I forgot to mention one point, is that there is a trivial with entropy, which is already well known, is that if, I forgot that, so sorry. So if you have a finite set with orthonormal embedding, okay, so essentially phi of x transpose phi of y is just 1 of x equal to y. Then what we have seen, like first lecture, is that phi of x transpose is diagonal. Okay, and since diagonal, then all my sigma p will be diagonal, all my sigma q will be diagonal, all the plane with eigenvectors will be solved. Okay, and at the end, everything we simply depend on the diagonals, and I will get that d of sigma p sigma q is the sum over x of the diagonal element for element x, which is just p of x, log of p of x minus log of q of x. Okay, so this is the true entropy, or true relative entropy, and it's well known in quantum mechanics. Okay, if you reduce to pure states, you get true entropy. Am I correct? Or?
I think it's mixed. No, it's I think it's actually mixed states that, like if you have just classical probability distribution, so it's just mixed states. Yeah.
Otherwise it's one, yeah.
Okay, so I'm sorry to, I don't know exactly the details here, but this is like, we know that for a particular case you get equality here, and we try to do something similar. Okay, so let me start again. So I have this divergence, which I write explicitly as divergence, the fundamental entropy between the integral of phi transpose and the integral of phi transpose for q, but I'm just putting p over there. So what I have here is the integral, okay, of the expectation over dp here and the expectation over dp there. So then my function d is jointly convex with respect to the two arguments. So by Jensen's inequality, it is less than the integral over d of the elements over there, phi of x transpose, phi of x transpose, dq over dp of x times dp of x. This is just Jensen, okay? But here, importantly, this is Jensen for the joint, for the function that depends both on this one and this one. Okay, if I just get convexity with respect to one argument, it won't work. It's joint, it is a joint convexity which is important here. And now I'm in good shape because this is a rank 1 operator. This is a rank 1 operator. So I know the eigenvectors, they are proportional to phi of x. I know the eigenvalue, they are all 0 and phi of x squared. And this one, the eigenvalue is all 0 or phi of x squared times dq over dp of x. This is just the, like I compute, so I can take this, since they are along the same eigenvector, this is equal to integral of, so I have to compute eigenvalue of p log of the eigenvalue of p minus the log of the eigenvalue of q. So I get integral of phi of x squared log, and I get p over q, I get log of dp over dq of x times dp of x. And now, because I've assumed the features are bounded by 1, this is less. So I can remove this, and it's just exactly the relative entropy. So what I've shown, like in 2 lines, is that this new notion of kernel entropy is in fact a lower bound on the true entropy, and the only assumption that the features are bounded. And even by homogeneity, it has to be the case, okay, otherwise. So this is like invariant by many transforms, and this was not, so you have to put some bound anyway. Okay. Let me check if I've not forgotten something. So this is, so compared to the discrete case, you just get one direction, okay, and
Negative sign?
what?
I'm not sure. Oh, okay. You have flipped the dq and dp. I haven't.
Yes, so there was like, you do p over q, and here there was q over p, and I inverted it. Okay. All right, so now we have a lower bound. So you may ask yourself, how tight is it? So here I will not do the math, but so here I will just highlight. So what we can show is that, so let me just like highlight the proof taking because it's kind of nice, is we will have to check whether this is far from that. And what we will do a quantum measurement. Okay, quantum measurement. So really leveraging that if you have a data processing inequality, if you measure something, you're going to reduce the entropy, okay? And we're going to start from that, do some measurement, and get to something which is lower, and that will be our lower bound, and that lower bound can be computed. And let me give you the measurement. So what is a measurement in quantum mechanics? So you get a trace between your operator and some measurement operator dy, and d of y. So d of y has to be PSD, okay, and symmetry and so on. And to get a proper measurement, you need that the integral of d of y is equal to identity. Okay, and so what we will do, okay, and we will define so uniform measure, let's call it tau. D2 of y being identity. Okay, this will be the uniform measure. And once you have that, you define q tilde of I, measurement at point I of the same thing, trace of sigma q dy, same measurement. What you know from quantum mechanics is that the divergence between sigma p, sigma q is bigger than the KL between P tilde and Q tilde. Okay, so this is just like essentially a data processing inequality. Okay, quantum version. So if you know about this, this is classical. If you don't, you have to look at it. And the fun part is that I took my undergrad book from quantum mechanics from Polytechnic, and this was in it. So you should always remember your undergrad classes, even if it's long ago. And so now the question is how to choose d of y. Okay, and I will not describe it, but you can choose d of y so that p tilde and q tilde are just smooth version of p and q. Okay, and I want to preserve some time for further developments. Okay. And so at the end, I'll just give you the result. Okay, the final result would be that at the end, dp, no. You can have a dpq minus d sigma p sigma q will be okay. It's will be small, okay, and I will not give you the details, but essentially the bigger the kernel, okay, the better it is. So if you have a kernel of the form exponential minus x minus y 2 over sigma, Okay, so essentially this will be a big O of sigma square. So I will not give the details, but this is just like defining a good D of Y and then specializing to those kernels, and you get like that. If the bandwidth goes to 0, then you get a better and better estimation. Okay, so I won't do it because it's going to take too much time. It's just to highlight the fact that, so of course, the smaller the sigma, the more n, bigger n we need to be to estimate the entropy. There's no magic here, so if you want to get tighter and tighter, then you need to get a smaller and smaller bandwidth. Any questions on that part? This is the key part, okay? This is how we think that the action is. It's just convex.
So you're just like sandwiching, you're saying,
Yeah.
you know, if P and Q tilde can just be made to be like slightly smooth versions
Yeah,
of P and Q.
exactly.
You get the lower bound and the upper bound, and I mean.
Exactly. And in fact, yeah, exactly. I take 4 lines, but I would need to introduce like more notations. But it's really the idea that you get a sandwich, and I try to prove like a sandwich with more direct ways, like convex analysis way. It took me like 10 pages, and with that simple quantum trick, it takes you like 5 lines. So quantum works, yeah.
I have like this question. I think I'm getting kind of the overall direction,
Yeah.
but maybe would you have some like simple example of something that with this you can solve, and with the previous relaxations or previous methods you couldn't? Just to get some intuition.
So intuition. Let me give you one. Okay, 1D, and with polynomials, with the trigonometric polynomials.
Okay.
So like example. Okay. So you can take, let's take x being 0, 1. Okay, and let's take phi of x being my favorite like feature space. Okay, and if I want to make it a kernel, I have to multiply by the Fourier transform of the kernel. Why? Because the phi of x transpose phi of y, okay, would be sum over omega in z of q hat of omega exponential 2i pi of omega times S dot transpose x minus y.
And Q hat is.
Q hat will be essentially,
this is
and this will be
that's the definition.
q of x minus y. And you recover your translation invariant kernel on the torus. Okay, so this is just one phi of x. So what is sigma p here? What is sigma p here? This is just it's an infinite dimensional matrix indexed by z. Okay, the frequencies, and this is the expectation of that. So you get the integral over dp of x. So I do the physics way, I put the dp of x before, okay, and then you get e of 2i omega pi of x times omega minus omega prime. I'm just taking the omega prime element, and what is this? This is just times q of omega. Times q of omega at 1/2, q of omega hat 1/2 prime. And what you get, you take the integral, you get the characteristic function of p. So you get p hat of omega minus omega prime times q hat of omega 1/2, q hat of omega prime 1/2. So you recover the similar Toeplitz matrix you get at the end, the diag of q hat 1/2, cubic Toeplitz matrix type diag of q hat 1/2. It's similar what we had before. Yesterday we had only omega was not z but just a finite set, and q hat was 1. Okay, and we only got the Toeplitz matrix. Now we get the we need to seem to work with infinite dimensional object, we cannot just let omega go to infinity, but take all the omegas without constraining. Otherwise, we get like an exploding matrix. And what essentially I'm saying is that essentially the trace of sigma p log of sigma p will be related to entropy. Okay? And in fact, if you are people that know about the equivalent between copies matrices and settlement matrices, it's not surprising because in that setup, it's known that if you take q hat of omega being 1 and then 0, this is a classical result that by Sego from long ago, saying that if you take that two-piece matrix, okay, truncate it and take eigenvalues, the spectral measure is the 1 of p. Okay, so this is well known. This is a classical result from analysis from like long ago, and this is just an extension to all OQs. So by computing the two-piece matrix with a characteristic function of p hat, the Fourier transform of p, you get information on p. And it turns out that everything is in the spectrum, okay, and you can get the entropy by looking at eigenvalues. This is just one example. So you're going to, instead of working with p of x directly, you're going to work with p hat. I'm not sure this gives you more intuition, but.
And so what can I do with that?
What I can do with that is that now you give me p in one way or the other, I can give you estimators of the divergence with p and q. So many people want to estimate information theoretic quantities based on various information about their measures. This provides you a way. For example, if you do like people use those divergence MMD. People use MMD, for example, to do like fitting of distributions. So they have to compute MMD. So you need to be able to get the MMD. If you prefer to have some information theoretic value to what you're doing, then you will use something of that kind. So it's just a different use. But then, when I go back to duality, you will be able to compute the log partition function, because you know how to compute dpq. In fact, let's do it now. The key here is that d sigma p sigma q is less than dpq. Okay. All right, so almost done. So remember that we define epsilon log of the integral, and with a plus sign, sorry, again, dqx as a sup over p of the integral of p of x h of x minus dpq. This is a relative entropy. So what we're going to do, we're going simply to replace this by d sigma p sigma q. Okay, and we're going to so here replace this by essentially the integral, assuming that h is representable, that integral of a trace of h of the integral of p of x transpose, which is the trace of h sigma q. And we're going to replace this by sup over p, but only the sup over sigma p. Okay, and sigma p being what we know. So sigma p should be a moment matrix, and we know that we have a good estimate of the moment matrix, and this would be our k hat from before. Okay, so we're going to assume sigma p is PSD, and sigma p is in the affine hub of k. Okay, so this is exactly the SOS laxator that we had from the last 2 days. Okay, so this part is classical, and you see exactly what we did. So the epsilon is 0. If you remove that part, you see exactly what we did before for relaxation. what we are just changing is the fact that we add that term, okay? So we end up with sup over sigma p in k hat of trace of h sigma p minus epsilon d of sigma p sigma q. And now what you have is something which you can compute, okay? If you add some issue, this you can compute with in polynomial time. I won't give the details. It's computable and it's an upper bound on that. Okay? So here the key was, and this will be important for all later developments, is that we get upper bounds on the lower partition function. So the whole goal of this last half hour is now we get a variable upper bound on lower partition functions, which can be computed. And this is very much in the same spirit as what Martin Wainwright, Mike, and others, many others have done. Is simply now using tools from the fundamental entropy as the way to get this variable upper bound. And so, for example, in the paper, I take a very simple function in 1D, and I get upper bounds of that kind. Okay, so this is just to get computed in practice. Alright, and one other thing is that, of course, in fact, the way I came to that is that often, if you want to solve the SDP from yesterday, you add that term as a way to score smoothing. Okay, so the traditional ways of solving SDP is to add the fundamental entropy as a regularizer, then the dual becomes smooth and things are easier. So in fact, you will do that anyway to do algorithms, but it turns out that that operation has also some information theoretic properties. And now I'm going to mention just extensions. It's running out of time. So a few extensions. Extensions. So first, there are many open problems, okay, in terms of how well do you approximate entropies? Okay, this is how well you approximate on some x, but it's unclear at the moment. But let me talk about extensions. So first, all F divergences. So if you don't like KL, but you prefer df of pq being the integral of f of dp over dq of x dq of x, okay, with f operator convex. So if you know what this means, it's okay. If you don't, then essentially you're going to trust me on KL is one of them, Pearson, chi-square is one of them. Okay, so all well-known F divergences are that form except total variation. Okay, so if you prefer to estimate, okay, I've done it, but Pearson, chi-square, others, exactly the same. Everything applies. Okay, so this is something which is also Ellinger. So everything works out. Second, a fun property, d sigma p sigma q is convex or concave in the kernel. Okay, so one weakness here is that sigma p is the integral of phi of x transpose dp of x. So of course this depends a lot on the kernel. Okay. And it turns out that since we have a lower bound, or here we have an upper bound, we would like to maximize the lower bound and minimize the upper bound. Okay, so Mike taught me well. And if you want to maximize the lower bound, it's better if it is concave. Okay, And in fact, it is concave. It is concave in the kernel, totally non-obvious. Okay. In fact, I thought it was convex. I had a MATLAB proof for convexity, but I messed up my MATLAB proof. And when I was trying to show convexity, I found a proof, but Jensen somehow was in the opposite direction. And after a while, I realized that I had made a mistake. It was concave.
So what does it mean concave in the kernel? So
Concave is mean that if you take this as a function of k, okay, so if you change the kernel, you change phi, okay, so that quantity will be different. For example, if you replace phi of x by let's say lambda 1/2 of phi of x, okay, so you take your feature map and you multiply by PSD matrix 1/2. So the kernel k of xy is phi of x, the new one is phi of x transpose lambda phi of y, k of lambda. And now if you take the new sigma p and sigma q, and the function of lambda, this is concave. This is not obvious, not obvious to me at least when I looked at it. So this means you can optimize it. So you get better and better bounds, and in the paper I show that you do get improvement, okay? And same thing here, if you can, this ends up being convex in the kernel as well, so you can minimize the lower bound. So this is like one fun aspect. Other fun aspect, and this is like using a better KL. Okay, so I sent this to a friend, but to a colleague in quantum computing, like in Lyon. He told me there's a much better divergence for you, and the divergence is, so you replace trace of A log A minus log B by trace of, okay, let's be careful, trace of A log of B minus 1/2 A B minus 1/2. Okay, and this one, okay, so if A and B commute, it's the same, okay, but it's not the same, and it turns out that, in fact, you can show, like this is like many papers in quantum like information theory, that this is always less than that, okay? So since I have lower bounds, then this will improve my lower bounds for free, and it turns out that all the developments have at least the upper bound aspect is also true for that one. Okay, so you get like this one is the entropy by Matsumoto. So this is quite recent, Matsumoto, 2015, and this one is you get an improvement, okay, for free, and even better. So if you look at this problem with like a chain of variable, this will be cancelled here, the chain of variable. And you get linearity in lambda there, so it's even easier for optimization. So this is like good to have colleagues in all areas. And then a last extension, which is the last one there, is so what we have is that we show that d of sigma p, let me formulate this correctly. Yes, so we show that dpq was bigger than d of ab if sigma p is equal to a and sigma q is equal to a. Okay? AB. And what we would like to know that is it the best lower bound? Okay. So what you're tempted to do is to take a supremum there over P and Q. Okay, such that sigma P equals A and sigma Q equals B. Okay, so if you can solve that problem, supremum over all P and Q, so that sigma P is A, sigma Q is B, of that, sorry, we want to find again inf over dpq, so that sigma p is equal to A and sigma p is equal to P. Okay, so we call that D star of AB. And if our goal is to get lower bounds on dpq based on the knowledge of sigma p, sigma q, this D star is the optimal one. Okay, so this is the optimal one. And it turns out that you can compute this using sum of squares. Okay, so you can use it, you can computable by SOS. When I say in quotes that if SOS is tight, it's tight, and if SOS is not tight, it's a relaxation. Okay, so it's going to be tight for the cases I've mentioned, like polynomial sigma D and etc. But just to highlight the fact that this is one other way. And I think I'll stop there for that part, and then maybe summarize in a few minutes what we have seen for the class. Are there questions on that last hour? Yeah.
So you wrote on the board this identity between the tail divergence and the log sum x.
Yeah.
If you replace by an divergence, by a general F divergence.
That's a very good question. So what you obtain is, so you would obtain the integral of f star being the potential conjugate of your f of h of x. dq of x. Okay. And for the entropy, f is p log p, and this is exponential. Everything is. Okay, so just to get back the entropy, f has to be t log by u log u, and f star is exponential, so everything works out fine. So it's not as useful because when f star is exponential, using sampling is very bad because of the exponential. So if you use f star, which is like not as exploding as the exponential, you can do sampling and you're fine. So it's really important when f star has an exploding behavior. So let me summarize briefly what we have seen, and then up, and then we stop exactly on time. So the key. So the last part I think is more like for fun. The earlier part I think is more important. So what we did. So we have int of x in some x of h of x, and we had two dual views sup over c of c such that for all x, h of x minus c is PSD, and we simply say that we replace this by sum of squares, so phi of x transpose phi of x when a is PSD. So this is a primal view, and we have the dual view, which is the inf over the trace of sigma h. Okay, when sigma was in the hull, the convex hull of phi transpose, and this was less than, bigger than the inf of trace of sigma h for sigma PSD. This is the Swarovski component, and sigma in the affine hull of K of phi transpose. Okay, so this is a key sum of square business, which is a primal view, dual view, and with classical tools, there is a discrepancy there, which has to be corrected by embedding phi in a bigger problem. This is the hierarchies. But if you take phi already like infinite dimensional, like with kernels, this becomes an equality, but you have to deal with the fact that phi is infinite dimensional by using like subsampling and controlling with the trace. But this is using kernels, it was the extension to kernels. And if you want to add here minus epsilon d of sigma times something, this is where you get the link with entropy. And on this, I will stop and take last questions before we go. No? Nati?
So, in all cases, you get exponential dependence in the dimension. If your invariance in low-dimensional manifolds in a high-dimensional ambient space. Presumably, you can adapt to this dimension of the manifold. Is this?
That's a very good question, and so the question is if I happen to be in a low-dimensional space, okay, for the measure, for example, then can I adapt to it? The answer would be kernels typically do, so it should work, but I don't know. I suspect it is true, but I am not sure. Very, very good point. Also, if h, something which is not true, is that if h, if you want to minimize h, and h happens to depend only on a small number of variables, then we won't find it because kernels are not well adapted to find like latent variables. Okay, so thank you very much for your attention and enjoy the rest of the school.